at n plus pi, that would, you know, sort of be another pole. And then if you sort of even if you try to jump, even if you try to, let's say, jump over this alleged pole, the integral you get for this jump, so integral over what I'm writing is gamma there, that thing is going to diverge. So I did so many of these calculations on my own because I was working hard on this problem, trust me. So that's why I'm saying, you know, this method is not the most obvious, but it's also the more elegant for that reason. And as you'll see, we're going to take the limit as n goes to infinity. Now let's see how all of this works out actually, because enough words, I'm tired of speaking, I need some action. Am I right? So what I'm going to do, I'm going to label these segments. So I'm going to call this segment 1, segment 2, segment 3, 4, 5, and 6. Trust me, we could have had way more segments. I've had to deal with 10 segments before. I'm also going to do those questions, so don't worry. So now segment 1, the parameterization is quite simple. Z is negative x. We're going to go, and maybe I should label the, so this is going to be a circle of radius epsilon. So it's minus epsilon, that's plus epsilon. I'm talking about those boundary points right there. So if we do that, we're going to have an integral that's sort of going from minus, or rather n, because of the parameterization, from n to epsilon, and then we're going to have 1 minus e to the minus 2ix divided by sinh squared minus x, and we have a minus dx like that. Well, sinh of minus x is minus sinh, but we're squaring it up, so that doesn't really change much for us. That's something that's really nice about this denominator. That seems kind of bothersome at the point. That's segment 1. What about segment 2? Is this circle, right? We can really parameterize on a circle, can't we? So on the circle, we can parameterize as z is, and maybe I should choose a different color. I don't want to keep confusing people. Epsilon e to the I theta. But notice the orientation right here is clockwise. So we're going to have a minus sign, and we're going to go from 0 to pi. 1 minus 2 I epsilon e to the I theta. I'm going as slow as possible. I don't want to lose anyone. This problem or this solution is elegant, and I want everyone to appreciate the beauty as I have. Now the great thing about this is that we can really simplify this limit, because we're going to have to take the limit as epsilon goes to 0. So what's going to happen later on is we're going to have to take the limit as n goes to infinity. Of course, as I said, it's an infinite contour. We agreed on that before. Why is it infinite? Well, I will answer that question shortly. I'm gonna lead by example. And then epsilon goes to 0. So these are the limits we're going to have to consider later on. Not now, I'm just writing it in normal terms. So what happens here is we can sort of use a property that sinh u over u as u goes to 0 is 1, and the square of that is also 1, obviously. So we can use that to sort of replace the denominator in the limit. And this is a common trick when we have a multiplicative factor like that. Simply replace it. Advantage of that is some epsilon and e to the I theta factors cancel out nicely, and we're just left with 1 minus e to the 2I epsilon e to the I theta over epsilon e to the I theta, and this I will, I think, come outside. D theta, that we can take the limit inside, boundedness, continuity reasons, and it turns out we have to do a L'Hopital rule because it's a 0 over 0 situation clearly. Okay, so we get minus 2I e to the I theta over e to the I theta, although we still need to integrate from 0 to pi d theta. So that cancels out and we just get minus 2 pi. So the contribution is non-elementary, that's all I'll say. It's non-trivial for 2. Kind of like the sine x over x. So you can probably call it Cauchy principal value or whatever, but that's what we get. Moving on to part 3 now. Segment 3. Segment 3 is actually the easiest segment of them all. Segment 3, z is equal to x. So all we're doing is we're going from epsilon to capital N. 1 minus e to the 2ix over sinh squared x dx. And now we're just going to keep it as it is. What we've done is we've taken the limit as epsilon goes to 0 already. So we might as well substitute instead of epsilon here. We can just make this 0 because we've already taken the limit for segment 2. So I'll just do that. We haven't really tampered with n yet. Okay, fair enough. Now, what should we do? Well, we have to consider segments 4 and 6 before we sort of consider 5, because that's the most important segment. Segments 4 and 5. So as you can see, I've sort of rewritten a few things here, trying to clear this a little bit more. So let me recap. We have 1 for segment 1, that's well parameterized. We took the limit as epsilon goes to 0, so that changed this epsilon to a 0 here, and that's because we were taking the limit here, and that this is part 2, giving us a non-trivial answer of minus 2 pi. And then the third bit, which was the easiest bit of them all, just direct parameterization, z equals x. Now part 4, the reason I had to sort of rewrite this a little bit is I want everything to be on the same page. I don't want to confuse people, because part 4, mainly part 5 is going to be the hardest. So on part 4, notice what's happening here. So the real part is the same. Imaginary part is increasing from 0, because we're on the real axis down here, and then increasing up to give us n plus 1/2 times pi. So the parameterization likewise is not hard. Real part is fixed, n plus say iy, dz is I dy, and the integration will go from 0 to n plus 1 n plus 1/2 pi, because that was the final height here. Okay, now we're gonna have, let's see, 1 minus e to the 2I n plus iy divided by sinh squared of n plus iy, I dy up front. Okay, let's keep this as it is. We can't really do much. We can probably simplify a little bit more, nothing beyond that. 1 minus e to the 2in e to the minus 2y divided by sinh squared n plus iy and a dy. Path 6 is actually similar. In this case, the real part's minus n, and it's a decreasing segment. So we're going to have a minus integral from 0 to n plus 1/2 pi. So I comes outside, 1 minus e to the 2i minus n plus iy divided by sinh squared minus n plus iy dy, which we can simplify a little bit more, and we're going to just keep this part as it is because the limit is going to come soon. We're going to have to take the limit soon, but not quite yet. E to the minus 2y divided by sinh squared minus n plus iy dy. Fair enough, fair enough. Now path 5. It's probably the hardest part of this question at least. So let's see. On path number 5, the imaginary part is actually the same and the real part is changing. And we're going backwards. We're going from n to minus n. So the parameterization, and I'll do this on a fresh page probably, is going to be, let's see, the real part is changing, so we're going to have x plus n plus 1 over 2 pi I. That's the imaginary part that's fixed on the top segment. And then of course we can consider dz as dx, so then no problems there. We're going backwards, so minus, from minus n to capital N, because that's what the length was of the horizontal segment on the top part. 1 minus e to the 2i x plus n plus 1 over 2 pi I divided by sinh squared of x plus n plus 1 over 2 pi I. And let me remind you, n is an integer. He's a positive integer. Just by construction, n goes to infinity, and since there's the upper bound of integers, this is possible. Dx. Okay. Now the big thing is we have to notice the denominator. We can simplify that significantly more. So let's just see. Sinh of x plus n plus 1 over 2 pi I being squared. We can use the compound angle formula for the sinh, which turns out to be similar to its counterpart in circular trigonometry functions. So sinh x cosh of n plus 1 over 2 pi I plus cosh x sinh n plus 1 over 2 pi I, everything being squared. Now cosh of I times something is actually cosine directly, n plus 1 over 2 times pi plus, well, this is actually going to have a plus I alongside with it, I believe. We can verify that because sinh has this in it, and if we just substitute this with an I, this is almost sine. It's just missing this this factor of minus I in the denominator, I think. So, or rather, yeah, so it's my bad, it's missing this factor of I actually. But actually doesn't matter because it's sort of gonna go away anyways. Sine of n plus 1/2 pi, everything squared. Well, n is an integer, is a positive integer. Cosine of any positive integer plus 1/2 times pi is going to be 0. I hope you know this basic trigonometric fact. The sign will actually alternate depending on what integer it is. So we're gonna have minus 1 to the capital N I cos x. Well, this goes away because the other term went to 0. Being squared, this term will vanish. The I will become a minus cos squared of x. This is all happening in the denominator. So isn't that spectacular? Because now we can simplify dramatically to get minus n to n1 minus e to the 2ix plus n plus 1 over 2 pi I, which I can also simplify a little more. Maybe I should just write this properly. E to the minus, let's see, minus n plus 1 over 2 pi, I believe, yes. So that's being multiplied with this exponential divided by, so that this minus and this minus will, this minus and this minus will become a plus cos squared of x dx. And now I think is the perfect time to take the limit as n goes to infinity, because, and this is also a good time of showing you what really happens if we hadn't considered an infinite rectangle. So if we take the limit as n goes to infinity, this term will disappear. This term will disappear just because of exponential. This will become infinity and minus infinity respectively. So out of these two terms in the numerator, this term goes away because this has gone to 0. This term remains. So that just gives us 1 over cos squared x dx, which is precisely hyperbolic secant squared of x dx, which if you you can calculate your derivatives, refer to a formula sheet, is actually, I believe, hyperbolic tangent of x evaluated at minus infinity and infinity. Hyperbolic tangent is hyperbolic sine over hyperbolic cos. So it's just going to be this divided by that at positive infinity, negative infinity. At positive infinity, these negative exponential terms will decay, and we have to do a L'Hopital rule of e to the x over e to the x, which will be 1 minus, at negative infinity, the positive exponentials will decay, and then we have to do L'Hopital of these two terms, which will give a minus sign alongside. So that becomes a plus here, so that gives us 2. So that this means the top contribution is actually 2. So the contribution on path 5 is actually 2. It does not disappear, and this was the rookie mistake I kept making, because I chose a semicircular contour like that, and then of course I did not reason properly that the infinite closure I have is actually finite. It does not. It actually has a non-zero value. I kept saying it was 0, and I was getting missing a factor of minus 1/2, which I'm accounting over here with this 2. Now one reason of why I chose a infinite rectangle for a contour is because of this. You see, if n were finite, at least the height part of it, if this thing were finite, that would have caused problems right here. This term would not have gone to 0, and we would have gotten two separate disjoint integrals, one involving this 1 over cos squared, and then the other involving this e to the 2ix some multiplicative constant divided by cos squared, and that's a real pain to calculate. That's a separate integral in itself, trust me. And we also don't know if this diverges, if this converges or not. I think it definitely diverges. That's the great advantage of doing an infinity, an infinite height for our stuff. And as I mentioned before, we are not on any pole, because the poles of sinh z are at 0, I pi, 2 I pi. You see, by choosing n plus 1/2 pi I, so we have a 1/2 pi I off shift from the nearest pole. That's because if you sort of would have considered an indentation around the pole at the top, like this for example, if we were on the pole, then the integral clearly diverges, because the denominator has a square in it. It's not just not a power 1. If it were, then it would sort of nullify with this exponential part, or just the differential bit coming out, that would have worked out, but it does not in our case here. So those are the main reasons, and this is sort of non-trivial. Trust me, this is the most non-trivial rectangular contour, infinite height contour you'll ever encounter. The only issue with having an infinite anything is the residues are going to be bad. So for residue theorem, we have the entire contribution equaling 2 pi I times the sum of residues. Okay. Now the thing is, for the sum of residues, we have poles of order 2, because we have a sinh squared and the poles occur at 0. Well, we accounted for 0, so we don't need to use that anymore. They happen at I pi, 2 I pi, and so on. And the numerator is not challenging. We're not having a 0 over 0 situation when we take the limit, because this will become some e to the minus 2 pi or e to the minus 4 pi at all of these points individually. So there's no contest from the numerator. The only denominator is blowing up. It has a square in it. It's order 2. So it's an order 2 pole. So we have order 2 poles enclosed at z equals I n pi. N is 1, 2, so on. So to do that, an order 2 pole, we need to actually multiply by this extra factor and then find the first derivative and then take the limit of that. So z minus I n pi squared divided by sinh squared of z. We will have to take the first derivative of this and then take the limit z equals I n pi, and then we have to sum all of these up. So I've done this calculation really fast, and I think I can afford to skip steps right now, because it's really not that challenging to do. The residues are actually going to be, let's see, we're going to have limit I n pi sinh squared z minus 2i e to the 2iz z minus I n pi squared 1 minus e to the 2iz 2 times z minus I n pi, and I will shift this now because it's sort of exceeded the confines of the page, and then minus 2 1 minus e to the 2iz z minus I n pi squared sinh z cos z, and this was just the numerator, divided by sinh to the 4th of z. All of this can be nicely simplified into 3 disjoint terms. And we're all taking limit as z goes to I n pi. The third term is 2 times that z minus I n pi divided by sinh squared z. Maybe I can make a little more space, minus 2 times 1 minus e to the 2 iz z minus I n pi squared sinh z over sinh to the fourth of z. Well, you can use the same, sinh of z is asymptotically similar to z as z is small, or that kind of argument for all of these things. And you notice that this will sort of cancel out with what we have here. Meanwhile, this ratio becomes 1, and we're just left with minus 2i e to the minus 2n pi. That's the residue. We need to multiply 2 pi I and then sum all the residues up according to the residue theorem. So we have contour integral f of z dz is actually so 2 pi I and this, so 4 pi, and we're going to sum the residues. We're going to sum from n equals 1 to infinity, because residues of the form I n pi, we start with n equals 1, right? We start with I pi and then go to infinity, because we're enclosing the infinite contour now. We've already taken the limit at this point. E to the minus 2 pi to n pi. Notice this is a geometric series, because e to the minus 2 pi, e to the minus 4 pi, and so on, which is converging because e to the minus 2 pi is less than 1. We can use the formula directly. 4 pi e to the minus 2 pi over 1 minus e to the minus 2 pi. Okay, fair enough. We could probably simplify this a little bit more. E to the minus pi, I believe, and e to the pi, e to the minus pi. But the thing is, you add all the contributions up. We took the limit as n goes to infinity, so this is actually going to be infinity now. Same here. And the great thing about these guys are they sort of mutually annihilate each other. One, because the denominator grows larger, and other because there's like a symmetry going on between them, so they sort of regularize that way as well. So they go to 0 in the limit as n goes to infinity. So we can add up all the contributions nicely. I'm going to just write them up. You can. So the first contribution was the 0 to infinity bit, so 1 minus e to the minus 2ix sinh squared x dx plus 0 to infinity 1 minus e to the 2ix sinh squared x. The minus 2 pi, the indent over the origin, z equals 0. And then we have to also use the contribution, the 2 from the top. All of that is equal to 4 pi e to the minus pi over e to the pi. Like that. We can move the 2 pi over there. This becomes 2 minus 2. Let's see. E to the 2ix minus e to the minus 2ix sinh squared x dx equals the 2 pi is 4 pi over 2 plus 4 pi times e to the minus pi over e to the pi minus e to the minus pi minus 2. We can rearrange this a little bit more. This actually simplifies nicely, because 4 pi e to the pi minus e to the minus pi plus 2 times e to the minus pi. So I've taken a common LCM out here for the first two terms, minus 2. This is 4 pi e to the pi plus e to the minus pi, 2 times e to the pi minus e to the minus pi, minus 2. This is 2 pi because that cancels. And this you can compare with the definition of whatever we have. We can divide by numerator and denominator by 2 for each of these individual fractions, and you'll notice we get a cos pi over sinh pi minus 2, which is actually 2 pi cot pi minus 2. This was the left hand side, the right hand side. What about the left hand side? Well, notice what this thing is. It's e to the x plus e to the minus x. That's 2 times cosine of x. So you pull the 2 outside for both the terms. 1 minus cosine 2x sinh squared x dx. This, according to the double angle formula, is 4 times sine squared x over sinh squared x dx. So all we have to do is we have to divide by 4. So I is dividing everything by 4. Let me write this compactly. 1/2 minus 1 plus pi cot pi, approximate value of 1.0778, whatever.